When the waveform repeats every time interval, these waves can be classified as periodic. And these periodic waves can be characterized by either being regular frequency, which can be represented by F, or angular frequency, which can be represented by omega. In order to solve for wavelength, which can be represented by lambda, we have to take the velocity, which can be represented by v, and divide that by f, which is frequency. Parsees states, if the velocity of the wave remains constant, then as the frequency of the wave is increased, the wavelength length. In this situation, the wavelength would decrease due to there being more waves in the actual string to take up the space. Part D states the difference between the frequency f and the frequency omega is that f is measured in cycles per second or hertz, whereas the units for omega are blank per second. So, f represents regular frequency, which basically just represents any number of events per time. So for instance, like rotations per second. Omega, on the other hand, represents angular frequency. This deals with the rate of which an angle changes. So most of the time, if not all times, usually this is represented in radians per time slot. So for example, radians per second. In order to find the period of a wave, we can use t to represent the period of a wave and use the expression 1 divided by regular frequency since there are no angles involved. An expression that would represent the relationship between omega and f would be omega equals 2 pi f. This would be the case due to the frequency representing the number of rotations per a period of time. Two pi would represent one full rotation of a circle. Hence how we come up with omega equals 2 pi at frequency. We can find the angular wave number, which can be represented by k, if we take 2 pi, which represents one full circle, and divide that by lambda, which will represent a wavelength. The wave number can also be described as the number of wavelengths per unit distance, hence the equation.